Okay, welcome to another edition of the Henstitute. This one we are going to be talking about transformers. I am not talking about Optimus Prime or Autobots and Decepticons. I'm talking about these things right here. So a transformer is basically a device that can either step up or step down your voltage. So step up voltage or step down the voltage. Now, the reason it does that, or the reason why we need that, is let's say that you have something connected to a regular outlet. So our regular outlet here is usually 120 volts, and it is alternating current. And you want to charge the battery on your calculator. But your calculator does not actually need, so this is your calculator over here, your calculator does not actually need to have 120 volts. It only needs 6 volts. So what we do is when we plug that in, you'll often notice that you end up plugging in this big box that's connected to your outlet. That big box that's connected to the outlet before it comes over to your actual calculator is it's a transformer, and it's designed to step down the voltage so that you'll take your 120 and step it down to 6. And that's one of the reasons why we do it. We might need to do the opposite. We might need to take a low voltage and step it up to a higher voltage. We do that with power lines because if we step up the voltage, it actually, one of the things that Nikola Tesla noticed is that high voltage actually transferred better than if you had it at lower voltage, and deals with the power that you're actually losing. And we'll talk about that in a little bit. Now, my picture here is actually a step up transformer. So this one is a step up transformer. So this our calculator example is not going to work. So I'm going to go ahead and erase my calculator here. That's not the example we're actually dealing with, but I just wanted to kind of give it that particular example. So let's just kind of erase these, but those could be an example. So the basic idea here is, let's say that I have a alternating current generator here, and it's connected to a coil of wire. So I have some kind of setup over here, and I have a coil. Well, I know that there's going to be a magnetic field that's going to be produced through there. Now, the way they've drawn this with their magnetic field lines is they've drawn the magnetic field lines pointed downward in this particular case. Now, obviously, it's alternating current, so that means it's going to alternate its direction. It's not always going to be pointed downward. By connecting it with this iron core, what you can do is you can kind of control this direction. And so we'll actually get a magnetic field to travel through this iron. It'll stay kind of in a loop here. So it'll travel over this way and then travel up and then travel this way and so forth. And that's actually going to alternate. It's going to go back and forth. But if I then wrap another secondary coil over here, with a certain number of turns, if I have a magnetic field that's actually changing through there, it should actually induce some kind of EMF across here. So an EMF is actually going to be induced. And so by having the generator produce a initial EMF, initial electromotive force, and then this one is going to be induced, we can actually compare those two. So I'm going to come back to my equation up here. And so we know that the induced EMF up here is due to Faraday's law, and it's negative N times the change in the magnetic flux over time. Now, the induced EMF would be the stuff across our secondary coil, and this would be the N for the secondary coil, and then the change in magnetic flux through the secondary coil in a certain amount of time. The other one that we would have is we would also have an EMF produced by our primary coil. So, or actually it's going to be the magnetic flux produced by that, and it would be related to this. So this would be the magnetic flux on the primary coil, that change in magnetic flux. But one of the things that's kind of neat is these two are the same. And the reason why they are the same is because they're traveling through this same iron core. So there's nowhere else for a magnetic field, a magnetic flux to be created. So if I take these two equations and actually divide them, one of the things I'll notice is this part of the equation will actually cancel. And what I end up with is I just have the EMF of the secondary coil over the EMF of the primary. In other words, actually the source, and would be the negatives will cancel each other. It'd be the number of coils for the secondary divided by the number of coils of the primary. And ta-da, I have what we refer to as the transformer equation. Now, you'll notice that over here in the middle, I have that same equation. They've written it slightly different. They've written it with the P's on top and the S's on the bottom. It doesn't really matter because if I switch the ratio, they've also written it with V's instead of EMFs because remember, E stands for the electromotive force. I'm not a big fan of that term. It works well in this chapter because we're talking about a magnetic field or a changing magnetic field actually pushing the electrons into motion. So that's what's actually why we get a voltage being created. But this is the same thing as a voltage or electric potential across there. So we're going to switch back to just using V. And this is the basic idea. This is how it works. And so what we would find is if I knew the EMF across my original generator, let's say this is 120 volts, this is our outlet, I could figure out the induced. I just have to figure out what the ratio of the number of turns is. And so this one would actually be a step up voltage, so this would be higher. The other thing that's going to happen, if you notice in your picture, we actually have that there is going to be some kind of current going through here. So this is the current through the primary, and it's going to go basically wrap around and then come back. It's actually an alternating current, but just at that moment in time, let's say it's going that way, and then it's going to produce a current in this other one. So you're actually going to have, as the magnetic field goes up, we're going to have a current that's going to happen, and so we'd get kind of a current going around here and so forth. So we'd have a current actually flowing through this thing. Now, interestingly enough, the other concept that has to stay constant through here is you can't create something for nothing. So your energy has to stay constant. Energy is conserved. Is conserved. And if energy is conserved, then if whatever energy goes in has to come out at most, that's the maximum. So what we typically do is we don't think of it in terms of energy, we actually think of it in terms of power. So the power of the primary always has to equal the power of the secondary. At most, that's the best it can do. And if you remember from chapter 20, we actually had talked about power for electricity is equal to the current times the voltage. So this would be the current through the primary, and the voltage across the primary equals the current through the secondary times the voltage through the secondary. And since this has to stay constant, if I rearrange this equation, one of the things that you'll notice, if I bring my Vs over to this side and I bring this over to that side by dividing by them, then I end up with a different kind of relationship. I end up with the fact that the ratio of my primary to my secondary for voltage is actually the opposite of my ratio for my currents. So this would be the ratio of my current through the secondary divided by the ratio of the current through the primary. So this is also up here, and you get that situation. Really what it means is you step up the voltage or you step down the voltage, but if you step up the voltage, you actually cause the current to step down here. And if you step down the voltage, then you actually step up the current. And what we actually have found with high power lines is higher voltage causes a lower current to go through there, and that lower current causes a lower loss of power through those high voltage lines. And so that's why we transfer electricity through high voltage lines. So this is everything about transformers, and this is what we are finishing up this particular section on. So I hope you enjoyed this edition of the Henstitute. Have a great day.